For the second talk, we're very, very happy to have Ovidiu Savin from Columbia University. And I think he'll speak about an energy model for harmonic graphs with junctions.
Okay, thank you. Thank you for the introduction. Okay, so I would like to talk about a free boundary problem in vector valued setting. And let me write the title here. So I want to talk about some harmonic functions, graphs. With junctions. And this is a joint work with Silva. Okay, so the model would be like this. We think we have first n harmonic functions. I draw here the graphs, U1, and they are ordered, U2, so on, UN. U1, UN. Okay. And from an energy point of view, we think that, well, this configuration just minimizes the sum of gradient of Ui squared. These are harmonic functions. But then I would like to think of a model in which these harmonic functions prefer, I want to add something to this energy so that these harmonic functions, if they are close enough, they prefer to glue to each other and maybe separate later. Right. So, and you can try to think. So I want them to be harmonic on each component, but from time to time to have these junctions. So I want to add here a term, let's say a potential term, which I know by W of U. And basically, if I want them to be harmonic, I want this W of U to be constant on these pieces, right? But maybe change values to have a lower value whenever two graphs coincide. So then the natural choice for W of U would be, let's say, the cardinality of the set U1, U2, UN. So if I add such a term, then of course, instead of paying a value 2, if I have two harmonic functions over the full interval where I'm doing the minimization, then it's better for two of them to collide, at least in the middle, to pay much less for this term, and then maybe each one reconnect with boundary data. Okay, so let's say, so what I would like, and this is the model that I want to study. So we want to minimize among all functions. So this is an important, we want the constraint would be that U1 is bigger than or equal than U2 is bigger than or equal than U sub capital N. Let me write here, so actually capital N represents a number of different membranes, and let's say small n is the dimension. So Ui are functions from, let's say, the unit ball in Rn with values in R, and these are the graphs. I represent here the graphs. So there are two questions that I'm interested. Let's say question 1 for this particular model would be to understand the junctions, understand the regularity of the functions. Let's say understand the junctions. Exactly what happens when the membranes coincide. And the second question would be to understand the free boundaries. Say free boundaries. And in fact, there are n-1 free boundaries here. Say the boundaries that I denote by gamma sub I are the boundary of the sets where the Ui is bigger than Ui plus 1. So I think of this being elastic membranes, U1, U2, UN being elastic membranes, and I want to understand these regions where they separate. But because I have capital N such functions, there are n minus one free boundaries. And these free boundaries, let's say if I think I have two free boundaries in R2, you can think that this is gamma 1 and maybe this would be gamma 2. Or it would be interesting to understand how the two free boundaries interact and what sort of possible geometries there are. Let's say as a physical model, I mean, is this like a reasonable physical model? One way to think would think that these are elastic membranes that actually are glued to each other initially, and you try to pull them apart. So there is some sort of adhesive property, or let's say that they are wet, and you try to pull them apart or they stick to each other, and you have to spend energy to pull any two apart. So when there is heat, right? So it would be like this would be the physical interpretation of this model. Okay, so let me say a few general things about the model. What can you say? One can say from the very beginning that if you look at ui and you add the same function, let's say t times phi, with phi being a function with compact support, u plus t phi are still admissible. So I cannot, I mean, if I want to create a perturbation to this energy, because of this constraint, I cannot just perturb u1 and u2 arbitrarily, right? But on the other hand, if I perturb all the functions by the same side, the constraint is preserved. So this is an admissible perturbation independent of the sign of phi, if I add the same phi to all of them. When you look at the W term doesn't change. So when you look at what you get as you let t tend to 0, you get that the integral of gradient of ui dot gradient of phi, the sum, where all this dx is 0, which means that the sum of ui is harmonic. So what you can say from the very beginning is that actually it doesn't, independent of the junctions, the average is always harmonic and can be computed from the boundary data. Whatever boundary data you give me, I can immediately tell you what the average is, which means that in fact this is not a system of n, really of n equations, but rather of n minus 1 unknowns, right? You can always okay, so actually let me say one more thing. If somebody tells me that the function phi is harmonic, right, and I subtract the same harmonic function from the ui, actually the energy just changes by a constant. So the whole problem is invariant under additions to harmonic functions. So because of that, you can only subtract the average from all of them and reduce to the case. Let's say we can reduce to the case sum of the ui is equal to 0 to start. Okay, so what happens when you have, let's say, two membranes, right? If n is equal to 2, so from now on we're going to assume this thing here. So when n is equal to 2, this would correspond to a scalar problem. Yeah, so if n is equal to 2, you just have two functions. The one is the negative of the other. So then the energy is simply the sum of I have 2 gradient of u1 squared plus the cardinality of the set u1 negative u1. This is the energy. I mean,
you could put a constant in front of that. Would that change things?
If I put a constant in front of this?
Yeah.
No, because if I multiply the use by a constant,
Yeah.
sort of this remains the same and this changes. So,
Yeah, okay.
so the constant is not important. I mean, whatever constant it is, it can be again mod out by multiplication. So in fact, this 2 is irrelevant here. And the value of this is simply, I mean, this is simply 1 plus the characteristic function of the set where U1 is positive. So if U1 is 0, you pay just 1 for it, but if U1 is positive, you pay 2. You try to minimize this among all functions that are positive. So what this problem is known, let me rewrite this problem here. In this particular case, this is known as the one-phase free boundary problem. So up to a constant, the one-phase free boundary problem, you want to minimize the energy gradient of U squared plus the characteristic function of the set where U is positive. Dx. Yeah, so this is bigger than equal to 0, which graphically you can try to think corresponds to a situation in which you give me a function U that is, let's say, is 0 here, and maybe positive here. This is the boundary data. And then what you expect to get, a function that is harmonic wherever is positive. But then to have also a region where you might be 0, sort of where, again, you can try to think of a membrane that is glued to a table that you pull apart. And this is the part sort of that pulled up. And this is the region where it sticks to the table. And the Euler-Lagrange equation here is, so what you get that Laplace of U has to be positive. Instead where U is positive. Laplace of U has to be 0 when U is positive. And then you have that the gradient of U is prescribed, is equal to 1 on gamma, which is the free boundary, which is the boundary of the set where U is positive. In this picture, this would be gamma. And this is the free boundary because you have two conditions. You have that U is 0 to start with, but also the gradient is imposed to be equal to 1. Yeah, so this is known as the one-phase or Bernoulli one-phase free boundary problem. And this was studied initially by Alden Caffarelli in 81. They considered this problem and developed the basic regularity of the function U and of the free boundary. So let me just, because that's what we want to do more or less in our setting, what we have here, we have like a vector valued version of this problem, or in which we have like n-1 coupled one-phase problems, one on top of each other, that are interacting with each other, and we want to understand what happens with the free boundary and with the solutions. So before we go to the vector setting, let me just discuss a bit the scalar case. What are the questions or mathematical methods to deal with this problem? Yeah.
Is this related to what we call the wetting problem? Wetting.
Wetting. I'm not sure exactly what is.
It's a very similar problem, but you have an interface, and but then you have fluctuations you're allowing. So you're looking at minimizations, but sometimes you want to have allowing fluctuations. So
yes, there are, let's say one can do the parabolic version or maybe just look at critical points. I'm trying to do, let's say, the easiest of them all, just minimize the energy and try to understand the configuration. And this one-phase problem, where does it occur? So it occurs in jet flows, like in cavitational flows, in fluids, in flame propagation. So it appears in a lot of, let's say, basic free boundary problem because it's one of the, it's a basic model of a static free boundary problem. So what are the results for this case? The results for the one phase free boundary problem would be first you want to understand the regularity of the function u. So here there are no, I mean, everything is clear. You see that u is actually exactly as you see in the picture. U is Lipschitz continuous. Yeah, it cannot be better than that because you have a jump on the free boundary, and you can say that the Lipschitz norm of u in the interior is bounded by the value of u on the boundary. Let's say let me be here u in L2 or in H1, wherever the minimization makes sense. But the function is very nice. Then what you want to understand would be the free boundary. Of course, whenever I write here that the gradient of u is equal to 1, that would be if the free boundary is smooth. If it's not smooth, it's understood in some weak sense. And so the second part, how do you study free boundary? You do a blow-up procedure. So you start, let's assume that x0 is a point on the free boundary gamma. Here, like some x0. And then what you want to do, you want to create this blow-up limit. So you say, look at u of x0 plus rx divided by r. The problem is invariant under Lipschitz dilations. Yeah? So this would be the natural scaling of the problem. And what you can show that up to subsequences, this converges to some global minimizer u bar. As r tends to 0. And this u bar is, right here, so u bar is a homogeneous of degree 1 global minimizer. Homogeneous of degree 1 global minimizer. And we call this a cone. Yeah, this is a cone. So actually the strategy is exactly the same as in the minimal surfaces, right? That's exactly what you do in the minimal surface. You pick a point, you blow up, and there is a monotonicity formula called Weiss monotonicity formula. The monotonicity formula allows you to say that in the radial direction, the limit is trivial. And then you need to understand what are the possible blow-ups, the possible cone that you can see in the limit. And if you go in one dimension, well, there is only one answer in 1D, right? If I look at it and equal to 1, what I get a 0 on one side, and this, we just have x plus in 1D. And if you're like at a regular point, like it's shown on the blackboard, even if you're in higher dimension, you want to say that x0 is a regular point. Let's say x0 is a regular point. I'm going to write regular of the free boundary if up to subsequence u bar equals to, let's say, xn plus up to rotation. Yeah, so essentially say, well, if I see this picture after I blow up, if I see the one-dimensional picture, even if I'm in 2D or 3D, I call that a regular point. And then there is like an epsilon regularity theorem saying that if indeed your blow up, even up to subsequences, one blow up looks like this, then actually this thing is really a nice surface. Yeah, so there is this theorem that says that if x0 is a regular point, then gamma is smooth, is analytic surface near x0. Okay, and then what happens at the points that it might not be regular when you have a blow up and it doesn't look exactly like the one-dimensional profile, and you have this dimension reduction, just all this, yes.
Okay, so does it also tell you about how the two sheets meet? The other two sheets, is it just the boundary that's analytic, or does it actually, the whole original function is locally two analytic pieces meeting along an analytic curve?
Yeah, I mean, once this is analytic, the two harmonic, I mean, the picture, here they are not, I mean, here the picture is reverted with respect to x equal to 0. And of course, once this is analytic, this is analytic and you have 0. So everything is very extremely nice, like you would imagine. But then there is, again, like in the minimal surface theory, there is this dimension reduction, which says that, like Federer dimension reduction, which says that if there are singular points, then let's say that I'm going to say like this, that gamma is made of the regular part, which is whatever I described there, and then might have a singular part. Let's say this would be the singular part. What can you say about the singular part? This is dimension, Hausdorff dimension. So this is of dimension n minus 1, looks like a surface. But this is of dimension n minus k, where k is the first dimension, let's say dimension. Dimension, Hausdorff dimension minus k, where k is the first dimension, where a non-trivial, non-trivial cone exists, minimizing cone. Minimizing cone exists. And what I wrote so far is exactly the same as in the case of minimal surfaces. So the question remains, can I have other cones rather than the one-dimensional ones, at least in low dimensions? And if you look at the, just not minimizing, if you look at critical cones, there are some easy candidates for critical cones. This would be, for example, cones that look like this. Possible cones. If you, let's say here. So if you look in 3D, you can think that, like, if I put 0 on two such cones, and I look at the harmonic function homogeneous of degree 1 on the remaining part, this is a cone that is critical if I don't perturb the origin. And the question is, in which dimension are these minimizing? Okay. And it turns out that actually, if you go to dimension 7, n equal to 7, or let's say, then this cone, the radial cone, the radial cone is minimizing. But in dimension less than 7 is not. And then there are like some positive results, which says that actually if n is less than or equal to 4, xn plus up to notation is the only minimizer, is the only minimizing. Yes. So it's not known if in dimension 5 and 6, I mean, it's not easy to construct other example rather than the radial ones. So if you just look at the radial ones, it seems that dimension 7 is the first dimension which this will be minimizing. But if you try to look for all possible cones, you can only say it up dimension 4 is not, so let's say n equal to 5 and 6. It's like open. Not no. In the case of minimal surfaces, the dimension is sharp. This is like, as known that the dimension is 8. Within R8, you have Simon's cone, and up to dimension 7, ambient space dimension 7, the only minimizing hypersurfaces are just hyperplanes. Okay, so these are the sort of the results that one would like to understand for for such free boundary problems. Now let's move to the vector value. Okay. So before I discuss this, let me just mention a few works of free boundary problems in the vector value setting. So let's say some related works. In the vector, let's say some related work in vector. Yes. So there are here some works about 5-10 years ago. Some works due to Caffarelli, Chagolian, and Bieresian, in which they take the minimization problem with W of U being the characteristic function where capital U is positive, but no constraint. UIs are not constrained. UI, no constraints. So this is like you're looking at harmonic functions and you penalize if any of them is not zero. The only time when, I mean, what you want all of them to become zero at the same time. And only in that case, you gain something in the energy. This looks more like a scalar version for absolute value of U. Right? Like if I look at absolute value of U, does not necessarily satisfy an equation, but this, I would say, is a little bit closer to the scalar value of the problem. There is only one free boundary, which is the place where all of them become zero, or one of the components is different than zero. So the motivation for this would be when you look at cooperative systems involving species. Maybe the species cooperate together. Okay. Similar, I mean, sort of the same model is also considered by Mazzoleni, Terracini, and Belichkov. And it's also related, I mean, also when you end up with this, is also related to optimizing spectral functions. Like maybe if you want to add the first eigenvalues for a bunch of domains. Another model that was also considered was something in which you want the functions to have disjoint supports. So again, you look for harmonic functions, but you want them to have disjoint supports. This would be like when you have, instead of having cooperative systems of species, when you have competitive. So this is something also that Caffarelli and Pauli, in which you want the constraint UI times uj to be equal to 0 if I is different than j. This is the competitive systems. Or if you want, you can try to think that you have harmonic maps into singular spaces. And one model that sort of was the motivation for us in the end. So there was a model in which exactly our constraint was considered by Shipov and Vergara Caffarelli, which is known as the multiple multiple membrane problem. Let me explain in a second. So this is a model that they consider in 85. So the setting is exactly of n elastic membranes. This number 4 here. You have exactly the same model, like n-order membranes that cannot penetrate, but the potential term W of capital U represents the vector made of these components. W of capital U is equal to F dot U. So it's linear in U rather than being constant, as in our case. And this physically corresponds to elastic membranes being pushed against each other, and capital F represent the forces. So here you think you have, let's say, 2 balloons being pushed against each other, or 3. You have like a membrane and 2 balloons pushed from one side and the other, and you try to understand what happens to the free boundaries. Again, you have n-1 free boundaries. So like about 5 years ago, together with Huyu, we actually investigated this problem with this potential. This is a system of n-1 coupled obstacle problems. Yeah? So the one-phase problem and the obstacle problems, they are sort of similar in spirit, but of course one have similarities and differences. But I would say that after we did that, the multiple membrane problem, so what did we do here? We looked at the free boundary regularity, right? So here with Huyu, we studied free boundary regularity for this multiple membrane problem, for multiple membrane problem. And then we said, well, then we thought, what happens in the one-phase case? What are the differences? And then it turns out that there are quite different behaviors. What happens in the elastic membrane problem and in the case of harmonic function junctions that I'm discussing now. I'll maybe mention some of the main differences. So now I'll try to state our results. So here, start mentioning some results. So let me remind you, I'm going to write the energy functional in this form: gradient of capital U squared is being a vector. These are the sum of all the components squared plus W of U dx. And I write this W of U to look more like the one-phase problem. I'm going to write as a sum from n equals 1, from I equals 1 to capital n minus 1 of the characteristic functions where ui is bigger than ui plus 1. So essentially, I'm encoding if two consecutive members separate, I pay 1. If they're equal, I don't pay anything. Yeah, that's like the same as the cardinality of the set if I add 1 to all this. Okay. And also let me write some results. So we want to minimize, right, under this constraint. Some results. One can still say that U is Lipschitz. This is before. by a constant unit 2, capital unit 2. So I have the regularity for the functions is exactly what I would expect. So they are always Lipschitz and smooth wherever they in an interior of the region where they don't have any junctions. And also you can say that you can do a blow up. So the second part would be that if you look, so we always try to look at a point 0 that we assume that at the origin, so let's assume,
Sorry, minimizers always exist.
yes, yeah, okay, yes. So I apologize. Yeah, so minimizers exist because this just follows by direct methods in the calculus of variation. If you take like a weak, this function is lower semi-continuous. But what is important, this function is not convex. So you always get the minimizers, but you might not have uniqueness. And I'll give an example in 1D. Uniqueness fails even in 1D under simple, yes. So
One more question.
yes,
At a certain point, you have 3 layers. Each
Yes.
layer is an harmonic graph.
yes. I mean, it's not a harmonic. It's not a I mean, it's harmonic graph whenever they. I mean, they're going to have some junctions. Away from the junctions.
The point where there is nothing happening.
Yes. Yes. Yeah. Yeah. So, yeah. Let me just try to draw a picture, right? A 1D picture, if you want. You can try to think that you have a picture like this, right? Something of this sort. Yeah, so you can try to think this could be a configuration in 1D in which you have 3 membranes in which the top function does this, right? And the middle one does this, and the bottom one does this. So what I want to emphasize here that, for example, this piece you counted with multiplicity 3. The multiplicity is encoded in here. There could be some other model, right, related more like to geometric measure theory, in which you say, well, when 2 membranes coincide, the common piece may be counted 1 time. That would be a different model. In this setting, the multiplicity is according to how many. I mean, you count the energy according to multiplicity. What makes it collide is the second term, right? This is the one that sort of creates the.
So just for curiosity, as you said, you're taking the cardinality of the set, but could you, get the same result for just an arbitrary subadditive function, the potential? Because again, it's the subadditivity somehow, right, that is forcing the network structure to appear.
Yes, yeah, I mean, you can take more general, of course, if you take here something more general, you wouldn't have really harmonic functions. You would have depends what the derivative of W, right? I mean, if you give me, you're going to get the Laplace of UI is the partial derivative of W with respect to UI. This would be sort of the system that you have. And because here I really want to look at harmonic functions, I want basically this to be 0. So in other words, I want W to be piecewise constant. And that's why I'm doing this. But the other model, for example, the other model that I mentioned here, when you have forces, what you'd get a Laplace of UI in some senses like some sort of Fi, which is the force acting on each membrane, and when they would coincide, this force would change to being the average of the forces. So there are many more models. If you give me this constraint, I think what is very important is this constraint, that you want this constraint, and depending on what W you take here, you're going to have different models.
So subadditivity of W is not enough to assure a network type problem.
Subadditivity. Yeah, I mean, I think what you want, let's see. So what you want, let's see. So what you want, yeah, you want some sort of maybe convexity or something, not convexity, yeah. Basically, yeah, you want to be able to say that when you, I think under some mild assumption W of U, you can say you're going to end up with some sort of picture like this. Yes.
And you get also some angle condition from the stationarity. I mean, if you fix the boundary, you get a prescribed angle when you join together.
I mean, yeah, if we discuss, so let me say, let me go back to the model like this, right? Which is this, the one that I consider. So depending on the model, you get different things. Like when you deal with obstacle problems, you're not going to have angles. The membranes would come like this, they're going to intersect smoothly. But in this particular example, yes, you're going to have some Euler-Lagrange equation at the points that I'll mention in a second. Yes. So here also you can do a blow up. So let me go back. So just as in the scalar case, you can think, let's say you take 0 to be a point on the free boundary of U. And here I want to think that at the origin, all the membranes, all the functions coincide. Because like if I take, for example, this point locally, I can reduce it to say that I just have 2 membranes, right? Or like if I'm at this point, I have 3 membranes coincide. So without loss of generality, you always assume that at 0, all the membranes coincide, but away from 0, some separate. So I say that 0 is some sort of free boundary point. This means that it belongs to one of the free boundaries, but I don't know yet to which one, right? So if I'm in this situation, then I can do the same blow-up procedure that was written there. And I end up that after I blow up homogeneous of degree 1, up to subsequences, right? Up to subsequences, I end up with some global, this would be a global minimizer, global cone, which means it's a minimizer, it's homogeneous of degree 1, and so on. So now what happens in 1D, right? So
Just one moment, because I'm getting super lost. So now the absolute value of U, what does it represent exactly?
oh, I really mean that actually all of them 0. I mean like this, that all of them coincide at 0. I'm under the assumption the sum of the UIs is 0 at the origin to start. Let's say after I subtract locally the average. And I want to say that all the UIs are 0 at 0, right? So I want to say that capital U of 0
I see, but
is equal to 0.
and there's some way in which you can reduce any boundary, any point on the free boundary to.
Exactly. So if I'm here, I just subtract the average, and I think I just have only 2 membranes, and I reduce, yeah, so exactly. But yeah, this means that all the membranes coincide at 0. And 0, I mean, is not an interior point of the coincidence. So let's say in 1D, what happens is that there is I'm going to write here the Euler-Lagrange equation. So 1D, I'm looking for cones. Yeah? So let's say one situation is that I have some 3 functions here. Let me write multiplicity 3 here, and then things would separate like this. I would look at a triple junction. So what is the Euler-Lagrange equation at this point? If I just do domain deformation, so if I look at the graph and I'm just moving the domain deformation, the Euler-Lagrange equation says at such a point, it says that when I look on the right, the gradient of U squared has to be equal precisely with W of U. Yeah? So there is like a balance of energy. It says on the left, all of them are 0, but on the right, when I split, the sum, this is the sum of the squares, has to be equal to the value of W. In this case, W would be 2, because W just adds the sum of the characteristic functions. However, this is just under domain deformations. But what can happen here? So in 1D, you can think, what would happen with this situation? Going a bit slow, but what would happen with this situation when you give me three harmonic functions that coincide? On the left, they are all zero, but on the right, they have the value +1, 0, and -1. Then if you think you're going to have a triple junction, sort of what it says that, well, let's say this is 0. I have slope 1 here. I mean, I need to have slope 1 here and slope -1 there. That's exactly what this says. I want the sum of the slope squared to be equal to 2. The situation is symmetric, so I can only have 1 and 1. This is actually not minimizing. It's cheaper to connect two of them farther, like this, and do this. So it turns out that this symmetric configuration is not minimal in 1D if I'm allowed to change topology, and I am allowed to change topology because I'm doing the minimization under any deformation. So actually the minimizer of this symmetric configuration in 1D looks more like this. At the end of the day, you're going to have two minimizing. So one is going to start a little bit farther down. You're going to have one going like this. So this, the minimizer in 1D of this symmetric configuration would look more like this. And of course, there is also the symmetric one on the other side. So it turns out that in 1D, minimizing cones, I cannot have triple junctions in 1D. I can only split membranes in two, K on one side and then minus K on the other side. And you can say precisely with what slope. So I would say I'm going to write here the cones in 1D are of the type. I'm going to write here U1 equals U2 equals to UK. And the slope on the right is supposed to be exactly 1 over K minus 1 over N square root of this times X plus. And the remaining membranes, UK plus 1 is equal to so on is equal to U capital N. And these are have negative slopes. That would be exactly 1 over N minus K minus 1 over N over 1/2 X plus. So I can characterize all cones in 1D exactly as looking like K. I have here multiplicity K on the top, N minus K on the bottom, and all N coincides to the left. And I know exactly how the angles split from this original N. Okay, so, well, I don't have a lot of time, but now what happens? Well, then you can do an epsilon regularity theorem and say that actually also in higher dimensions, sort of the part, so let's say, so from here, you can, by doing like some sort of dimension reduction and so on, you can say that the picture that you see in 1D with these cones, you pretty much see in n dimensions almost Hn minus 1 or Hn minus 2 everywhere, right? That's sort of what you would see in 1D is generically what you would see in higher dimension up to a set of codimension 2. But then the interesting part, what happens actually when two boundaries cross, right? So to see that, you have to go to cones in 2D. I'm going to write here, I'm almost. Say cones in 2D. So actually we're going to 2D, there are some so there exists only one cone, so there exists only one minimizing cone. Okay, here 2D cones, I'm assuming that I have just 3 membranes. So I cannot do 100 membranes, so just 3 membranes, meaning I have 2 free boundaries, gamma 1 and gamma 2. And I'm interested in the points where these free boundaries actually cross themselves. So I say that happens at the origin. So there is only one minimizing cone, which looks like this. So it's actually very rigid. So the configuration looks like this. So I have here an angle of 120 degrees. Here, all the functions coincide, u1 equals u2 equals u3 equal to 0 on this side. Here I have like a 90-degree angle. This is gamma 1, gamma 1. Here I have something like gamma 2. So actually what happens is like this, that you have a configuration in which the free boundary gamma 1, let me draw it maybe with a different colors, I think. Gamma 1 is this, and gamma 2 is this. So actually when they intersect, they don't intersect smoothly. They intersect at some very rigid configuration that looks like this. Here I have 90 degrees, here 60. And your function u1 is made of 3 linear pieces. So u1 is linear here, 0 here. u2, u3, the bottom one is linear here and here and here, and u2, the one in the middle sort of has to split between them. But since time is almost up, let me just write a theorem. Essentially says that this is the only minimizing cone, but let me, and essentially what we can prove that whenever we have just 3 membranes and intersections, we look at intersection points. So let me write here a theorem. The last one. So we say if first we define a regular point, so we're going to say like this, a regular point of gamma 1 intersect gamma 2 is one point that when I do a blow up, I end up with a configuration like this. And this I can define even in higher dimensions. In the sense that when I do a blow up, I see this picture cross another n-2 dimension perpendicular to the blackboard. That would be a regular intersection point. And the theorem, it says that if I look at the full free boundary gamma, this is made of regular gamma 1, which would be like a smooth surface. It's like basically be like this. This would be like the part where I would see some sort of regular part of gamma 1, union a regular part of gamma 2. These are just the blow up at these points would look like in the one phase. Things would be very nice. Union a regular part of gamma 1 intersect gamma 2. This is supposed to be a C1 alpha curve or a C1 alpha submanifold of codimension 2, which would be some curve going to the blackboard like this. And then union some set of codimension 3. And the last thing I want to mention is that this alpha here actually has a precise value. Alpha is roughly like 0.36 and cannot be improved, which means that indeed when things intersect, I see this angle, but the way actually the free boundary will come towards such a free angle, adjust to it in a C1 alpha fashion, not in a smooth fashion, not in a C11 or C2. Yeah, so it's somehow interesting that the value of alpha is some number between 0 and 1 and cannot be improved, and it comes from studying some spectral problem for the linearized equation of this configuration. Okay, I apologize, I went a bit over the time. Thank you for your attention.
Any questions?
I mean, you said that the solution in general is not unique. right?
Yes,
So also in that case, if we do the symmetric, we have another solution, right?
exactly, yes.
Okay, but do you expect to be generic? I mean, if you perturb a little bit the boundary data, you get generic uniqueness for this problem?
Yes, I would expect that. I would expect that for any problem to have generic. Yeah,
Depends on the kind of perturbation you do, right? I mean,
yeah, I mean, of course, when you say generic, what does it mean generic and so on? But yeah, I think it's basically,
Well, no, if they're both minima, you would expect, if you perturbed it slightly, one would be smaller than the other, but they'd both be local minimum. Right?
yeah, I think, yeah, you have sort of two, you follow two different solutions and like two different curves of
Can
solutions.
you get critical points then, if you have two minima?
I mean, if you think you perturb them a little bit, one of the two configuration would be minimal while the other one wouldn't be.
Right, but
If, unless you
but it'd be
perturb.
a local, but it'd be a local minimum.
Yeah, it would be a local minimum, exactly.
So
Local,
the question was, if would you expect a critical point, that is, going to match a saddle?
well, I think, yeah, so maybe it would be more interesting, I mean, a lot interesting to study a parabolic version for this equation, right? In which, when you study a parabolic version, it would mean that actually you are going to see triple junctions and the things moving. So here we're just doing the minimizing part, and if you just insist on the minimizing, you sort of kill this triple junction and so on. But in the parabolic version, you would see more interesting, or like in the critical, just look for critical points, you'd see more interesting, I mean, richer, I don't know, richer family of solutions.
Well, actually, I go back to, I mean, I can see my perspective on these things is completely different. If you actually fix the boundary data and then you actually change the weight you put on then you could ask the question of what happens when you let that weight either become very, very, very small or very large, I mean, very large or very small. So you could ask what happens if you let the weight go to the weight you put onto infinity for a fixed boundary value.
Yes.
That.
Yeah. I mean, you can put sort of weights. I mean, you can try to think even in this model that each function has different weights that
Yeah.
sort of one membrane would count more in the energy than the others, and you start playing, and you can try to do like a whole continuum family of problems of similar type, but then you would change a little bit, like the Euler-Lagrange equation and the vertices. Yeah, but yeah, one can do that.
Because the question would be that if you don't weight different harmonic functions differently, but if you put let's say, a coupling constant, a private W, fixing boundary condition, and start moving the weight, would you see phase transitions? You look at
Yeah.
the minimizers.
Well, if you look at minimizer, I don't know exactly what does it mean, like phase transition.
So,
Like, yeah.
so you look at the minimizer for a fixed value,
Yes.
and you see, let's say, you see this picture.
Yes.
With,
Yes.
fixed number of nodes, or fixed number of components of the boundary.
Yes.
You start moving that constant, and
Yes.
that number will change.
Yes, I mean, the number of nodes, yeah, I wouldn't see triple, I mean, what I want to say, I wouldn't see triple junctions if I look at minimizers, right? I think that this is, because at some point I'm going to reach the situation which I'm going to have two different configurations with the same value. And if I look at the minimizer, I would jump to the other one, right? So if I just look at minimizers, there is a discontinuous way of jumping from one solution to another. But if I were to look like at a continuum version, like a parabolic version, then I couldn't do that. And that's exactly sort of what I said. It would be interesting to look at, yes.
So how much of this relies on the energy being, the first part of the energy being just the Dirichlet energy? If you were to put there something like square root of, something that has to do with the area, let's say.
Yeah, I don't think if it has to do with the area, I don't think a lot would change. I think, of course, technically it would be a little bit more difficult, but I think you'd see exactly the same, very similar phenomena if you put the area. If you put something here that would be not like Dirichlet, but it start mixing the U1 and the U2, really like making like a coupled system, then I think things would be maybe more complicated, yes.
So you're giving us a decomposition that seems to be, okay, full codimension 1, then codimension 2, at least I think you
Yes.
mentioned that, and then we have codimension 3.
Yes.
And this is very much related to, in fact, what are we studying? Like, the first thing is the most natural thing, then there is something that should happen in codimension 1 in the free boundary. And then one may argue that then the codimension 3 should come from 3 things happening together. We should have more or less that probability. Sorry, that codimension 3, which would suggest that if one is able to characterize or to say something, if it's possible, about 3D cones, one should be able to go on with this.
Yes, yeah. I mean, yeah, theoretically, this is what you want to do. Indeed, you want to understand this picture in more and more dimensions. And if you understand it really well and you can prove some stability of regularity, you can keep on going with this. Yeah, but I have no idea how to find sort of cones in 3 dimensions, right? In 2D, it's easier because it's basically a problem on the circle. And I kind of understand on a circle, I just have to solve some sort of linear function and how they split, but on the sphere is much more difficult. So I have no idea how to, how to understand. I mean, it's possible, but one would need to understand the cones, and I mean, I'm not sure. And for sure, I don't think it's easy to understand the cones in higher dimensions.
You don't expect them to be any more piecewise linear, for example?
Yes, I mean, yeah, the question, even is it clear that there are other cones? Let's say if I just look at 2 free boundaries, are there other cones in 3D that don't come just from 2D cross R? So that's not clear. Then there might be in 3D, this might be the whole thing. Or it could be a point where these things are not this cross R, but there are some sort of domains on the sphere that intersect in some I don't know, exact way.
We kept calling those membranes.
Yes.
So if you change this to an area function,
Yeah.
does it change much?
So that was like one of the previous questions. I don't think it doesn't change much. I don't expect it to change much. It's more technical because you have to worry about maybe gradient estimates for minimal surfaces. But in terms like when you blow up or what you expect, yeah, this is a model in which you simplify it very much, right? So membranes is exactly the linearization of the area functional, and just to simplify things.
Any more questions? Okay, so let's thank the speaker again.